Do you know the difference between HDL compiler and synthesis compiler? Do you know how synthesis does attach the technology node to your design? Do you know the various levels of abstraction in VLSI design and why all these abstraction levels are kept? Can you correlate the various levels of abstraction with the V-curve of the VLSI design? Stay tuned till the end of the video to know all the answers.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will introduce you to the concept of synthesis in VLSI. Next, we will discuss the V-curve of the VLSI design and you will understand the significance of synthesis through this particular V-curve. Next, we talk about what synthesis means in general. This point, we will discuss to generalize the term synthesis in the entire ASIC design. The synthesis at different point means different things. So, what does the synthesis mean in general? This should be in your knowledge. Next, we will talk about what is abstraction and we will talk about different abstraction level which you can correlate with the V-curve of the VLSI design. Next, we will talk about Y diagram, the coexistence of different domains. That means when we design, we do the concept to reality transfer of a design. And in that process, multiple domains are involved. So, the Y diagram helps us to correlate these domains. Next, we talk about mapping of levels and domains. This is the follow-up slide of the Y diagram or Y chart, and this mapping we will do for further simplification of the abstraction. That means now first abstraction we will connect with the V-curve, how the V-curve and the abstraction are correlated. Next we will talk about the Y diagram and the mapping levels, and then we will correlate it with the abstraction. So you will understand the VLSI design from a very bird's eye view. So this is why we have kept so many different concepts in this particular episode. Next, we will talk about the HDL compiler versus the synthesis compiler. Now, the HDL compiler is similar to the C language compiler which compiles the C language, but difference here, it will compile a Verilog code and it will not generate a kind of binary that is executable. Rather, it will do a HDL simulation. And we will compare it with the synthesis compiler, which is nothing but a compiler that transfers a HDL into a circuit consisting of different gates from the standard cell library. Next, we will discuss the VLSI design flow in both brief and detailed manner and position the synthesis inside the VLSI design flow. So that is the menu for today. Without any further delay, let's begin. Introduction to synthesis. Electronic design automation, that is EDA tool, plays a vital role in VLSI design by automating various stages of the process. EDA tool revolutionized VLSI design, combining human ingenuity with automation to streamline the synthesis cycle. So these 2 points basically say that the synthesis is done by a VLSI automation, and that is what we are going to learn in this particular series. Synthesis is a foundational step where the abstract hardware description language, that is HDL, also sometimes we say it as a Verilog, VHDL, system Verilog, is transformed into a physically realizable design, that is in terms of the standard cell library. We already have couple of episodes on standard cell in our channel. In case you want to learn about them, go ahead and search them either in the video list or in the playlist. Synthesis involves complex algorithms and optimizations. Consider factors like power, timing and area efficiency. So synthesis is nothing but a bunch of algorithms. While converting the HDL into a physical realizable design, it does a lot of optimization so that when it is going for fabrication, many problem complexities area that should be tackled in a much good fashion. In our channel, we already have a video about the power performance area, which is crucial to the chip design. You can go ahead and see that particular video to understand the significance of this particular point. Next, analysis and verification, that is the design verification DV phase ensures the correctness of the design through test, simulation, UVM, OVM, etc. the verification methodologies. So these methodologies for verification comes previous to the synthesis, just after your hardware design, that is the HDL design is prepared. So that is basically preparing the test bench and creating multiple vectors and then finding out whether is there any fault or any correction need to be done in your hardware language, that is either Verilog, VHDL or system Verilog. This comes after the design verification stage. DV phase identifies and rectifies functional, timing and logic discrepancies, thus enhancing the quality of the final product. So here we talk in detail from the beginning. That means as you are writing the HDL, that means either Verilog, VHDL or system Verilog, and then you are going for the verification stage, analysis and verification, that is the DV phase, where you are using multiple methodologies including UVM, OVM, etc. And this particular step helps in reducing multiple discrepancies and design faults. Now by this point you know that what things happen before the synthesis stage. Next we talk about the testing, that is the design for testability. DFT phase focuses on identifying and fixing errors that might occur during fabrication and manufacturing. Now here with this particular point we make a difference with the design verification. So there is another rigorous method for testing the design. It is called the DFT. So this is functional verification and this is fault detection. These are two different things, but they exist in the front end part of the VLSI design. Hence we have kept this thing here. We kept all the concept of the front end part here in this introduction because you should not get confused synthesis with any other front end steps, especially the DV or the DFT, that is the design verification or the design for testing. DFT phase subjects the design to various tests and ensure the resilience against fabrication anomalies. So the DFT ensures that the final product is good and all the fault testing is done before we leave the front end. Every aspect of the front end is verified and done. At some later point in this particular episode, we have the entire VLSI design flow as a flowchart. So there you will see what else are there in the front end part. And hence, as we discussed about the DFT, we talked about the DV, and hence you understand where the synthesis lies in the significance part of the VLSI design. And with this particular introduction, you are well able to differentiate the synthesis with any other important steps like DV or DFT in the front end part. Now here we are done. Let's move on to the next slide. V-Curve of the VLSI design. Before proceeding any further, I'd like to say that VLSI design is a very complex thing, and hence the complex thing should be subdivided into much smaller and easily doable steps. So these doable steps make the V curve. Now why it is V? Because we have a descending and the ascending manner of the design. So that you have to understand, which you will again correlate with the Y chart in upcoming slides. And why these are important in the synthesis? Because when you are talking about the synthesis, it consists a lot of optimization, and where those optimizations come into picture in upcoming episodes, you will see all those optimizations, their importance, their effects. But here in the initial episode, you should know about the V curve of the VLSI design, and hence you will be correlating all these optimization to the different parts of the V curve of the VLSI design. So let us start. The first step is system requirement. So this is basically a couple of checklists that generally when the design team sits, they talk with the company personnels, and they may include customers who are wanting the product, and hence pen and the paper we write down the requirement of our design, which is very much important. Now this requirement is first written on paper, then they are transferred into maybe in your laptop or desktop, and they are shared across the design team. So this is the first thing, the system requirement. According to that, the design team will think what to do. In the next step, when all these system requirements are in hand, what we do the design the system. So that means we do a top level block diagram of all the sub blocks those are needed. Here it is not visible completely, and I intend it to be like this because this is not a specific design we are talking about. Here we are talking about the methodology. Hence, multiple small blocks should be identified first from the system requirement and in the process of system design. So this is the system design. So we design the entire system into sub blocks, and sometime when these are realized, these are called sub chips also. the subchip may contain each block or maybe a couple of blocks together, depending upon what type of operation they are doing, whether they are analog, whether they are digital, or whether there is a mix. So this is the system design. Next, we have the subsystem design part. So here we design each and every subsystem. That means we put everything under the microscope. Like the scientist you can see here is seeing everything under microscope. So these are actually the designers. So there might be three teams in the design team. So first team take care of this part, a second team takes care of this much part, and the third team makes and concentrates on this particular part. So this way the subsystems are designed. Next step, what we design, you can see the graphics here, and we design the components. That means we further dissect each of these blocks into particular components. That means whatever components we need, we have to design. Here we have just shown the digital gates, but however, it not be only the digital gates. It could be a particular unit block, which may be a particular design block, which may have set of inputs and set of outputs as per the requirement we have set here. So it's very complex thing. You have to understand through this simple flow chart. So the design component part is then done. So we think of doing the tabulation of design components, and then the actual design team starts working to realize all these components. So this could be the standard cells, and you can see in our standard cell episodes that what are all there inside the standard cells. Not only the logic gate, there are a lot of other circuits, and in our channel we have already discussed about very complex things that are there in the standard cells. You can go ahead and watch those videos, and these components are realized by the design team. So here you can see a guy is sitting here and working in multiple computer monitors, and this guy is nothing but the designer who is now designing each of these components. There will be hundreds of designers like this in a company, and they will focus on different parts of the entire system. So design the subsystem, and when we break further down, we design the components, and the designer will realize the components. So your design might be a Verilog design. There might be 100 of Verilog definitions of the 100 different design components. Verilog designer has to design all of them, test them, and then they have to check their functional correctness also. Next, we proceed in the further step by build and check components. That means we build like this is a standard cell, this is a MBFF. We already have an episode. From there I have picked up this particular picture or the diagram, you can say. And then we have another standard cell. This is another thing we have already. This way we complete our checklist. That means whatever design components we have listed here, we complete our checklist by building and checking components. That means whatever steps are necessary to build those and checking those components by the design team. Next, we talk about build and check subsystem. So here, when the components are done, they are integrated together using the different EDA tools, and subsystems are built. So these are very complex things. Now to understand these things, we will further have a concept of abstraction. So in that particular slide, I will explain how this building system, subsystem are seen in terms of the abstraction. That means in a bird's eye view. So here we build and check every subsystem, or in case of an IC, it could be a subchip which is ready, and we test it with our digital test equipment. And then we move up, we have our board ready, and the processor or whatever circuit or IC which we are designing is ready, and we check the entire system. Now in this process, this checking process is called the post-silicon validation method, and we also have a video on that in case you want to learn about what is post-silicon validation. You can see we build and check the system here, and then we have a working system after this all checking are done. Now this is a prototype, not definitely the final product. This is a prototype, and this is also a prototype, the subchips. Okay, so once we go through this phase, we have a working system when all faults are found out and they are rectified from any and every angle. So we have a working system ready, and the designer says, yeah, now we have a working system. Now this chip is ready to go in the fab for mass production. So this is the entire VLSI design flow explained in a V-curve. So you can see it has a descending and ascending part. So this is the descending part and this is the ascending part. So why we have two parts? Because we keep breaking it down up to a component, then we realize component, and then we stitch them together to build the system. So we break it down first and then we join them and go up. This way the VLSI design works, whether it is a digital design or whether it is a analog design. Now here we are done talking about the V-curve of the VLSI design, and we go further in the abstraction level. There you also correlate with this infographics of the V-curve of the VLSI design, and then you will be well able to understand different terminologies that we are using in the synthesis, because the synthesis is just the beginning of the chip fabrication. That means it's the first step. Just after the design is done, this is the first step of the chip fabrication. That means you now thinking in terms of realizing a circuit on silicon. To understand that, you have to understand the complex VLSI design, and for that you have to understand the abstractions. We are done. Let's move on to the next slide. What synthesis means in general. Here we will have the terminology synthesis applicable at multiple points of the entire VLSI design flow. The flow chart you will be seeing after some slide, so don't worry about that. Here we generalize the synthesis. How and why? First of all, because you do not know whether you are entering into the front end or you are entering into the back end or you are entering into the standard cell design. There you may come across the synthesis term and you may get confused. So we are clearing your confusion at this very beginning. So here we have a table to explain what synthesis means in VLSI. In the first row, we will have the behavioral description. That means you write in terms of HDL or design specification or abstraction. And in the second row, we will have structural or realization. That means we have a structural form of the behavioral or the circuit realization. Now, let us see what will be there in the columns. The first column will contain about the logic level. That means what we mean synthesis in the logic level. Next, we will talk about what we mean synthesis in the circuit level. And in the final column, we will have the layout. That means what is meant in the layout level. So let us understand these things with the help of infographics. And we do not have any more text. We have infographics throughout the cells of this table. This is called FSM, and FSM concept you will come across in every digital design. Also from classroom text, you know about the Carnot mapping. So these are kind of behavioral description or specification of a behavior of a digital circuit that you can either realize in terms of FSM or Carnot map. So that is the level from which we are transferring it to the logic synthesis into a predefined set of gates. That means these gates are predefined in the standard cell library. From there, the synthesis algorithm will convert this FSM logic or the Carnot map or this kind of specification into a actual realizable circuit. So here it could be Carnot map, it could be FSM, and FSM has to be written in either of the Verilog, VHDL or system. It's not that FSM is itself a language. The FSM is a methodology. That methodology has to be written in terms of HDLs, and you may have also a Carnot map method. From there you write a HDL like Verilog, VHDL or system Verilog. And when you do the logic synthesis, this conversion process, you get the structural part in terms of logic circuits where the gates are pre-existing in the standard cells. That means your synthesis tool is well connected to your standard cell library, from where it is picking up the standard cell and placing them as per your design. So this is the thing. It is also a part of the EDA, that is the electronic design automation. So now you understand that you are at the first step of the VLSI design. That means the VLSI design automation. That means now your code, whatever code you have written, is entering into the first step where it is connecting to the standard cell library, which is well certified by the foundry and it is realizable in silicon. Now let us move on to the circuit level in case you are entering as a circuit designer. So we have our logic gates. It's a different notation. Why I have kept this inverter, you will see in the upcoming infographics. Now, when we want to convert this into a structural part, we go through the circuit synthesis process. And in that case, we transfer this logic gate into the transistor. That means we realize the logic gates in terms of the transistor interconnections in actual silicon. So these are also there from the foundry. Don't worry, these comes under PDK or DK package, and we have episodes on what is called PDK or DK. You can go ahead and see that episode in case you want to understand what is there inside the PDK and whether these things are not. So you can check, and we have demonstrated a free PDK in one particular episode. So there I have actually pointed out from openly available PDK. You can go ahead and see that. Next we have the layout level. In this particular layout level, what we do, we have this particular circuit here. So you can see this is going here and this is going here, and they are converting. So this is a chain of process in the entire VLSI design flow. VLSI design hence is a very complex process, and synthesis can mean different conversions at different points of the VLSI design flow. So now we have the transistor and we want to convert the transistors into something through a process which is called layout synthesis, and what we will get as a result is a transistor layout. You can see these are the layouts. These basic layouts of each and individual unit circuits, it may be logic gate or it may be a standard cell, so they are there in the standard cell library. However, when we have a particular circuit, say here I said it's of an inverter just to understand and correlate here to here and here to here, I have given this. But however, in actual case, what will happen that this particular circuit will be here and its corresponding transistor circuit will here, and it will go here and the actual layout will come here, and this layout synthesis will be done by your PNR tool. That will connect with your standard cell library, pick up the layouts of each and every cell, and it will do the layout synthesis here. And that has their lot of complexities and optimization at that level. I am not talking in detail about that because I have to make you understand what synthesis means at different points of the VLSI design, so that you have your mind very much clear about the word synthesis. In this particular series and in this particular episode, we will be entirely focusing on logic synthesis, and we will be not covering the circuit synthesis or the layout synthesis. We may have some later series on these topics, but not now, not in this series. We are done here with this infographics. Let us move on to the next slide. Now, what is abstraction? I have talked about the V-curve, I have talked about the different synthesis. Now let us see why the abstraction is there. This is a very difficult word even to utter, right? It has, I think, 3 syllables, abstraction. And what does it mean? So complex to utter, right? But this complex word makes the VLSI design simple. How? First of all, abstraction is a conceptual method used to simplify complex systems or ideas by focusing on the essential aspects while ignoring unnecessary details. That means you have a bird's eye view. I have shown in the V-curve, you have a block diagram of a entire chip, right? So they are unnecessary details. That means about the standard cell and their transistors, right? Those are not there. This is called the abstraction concept. The abstraction basically hides unnecessary things and keeps the necessary things in your table. Now to the V-curve, as you step down, you focus and zoom, may 10x zoom, maybe 20x zoom, maybe 50x zoom to get down to each and every component and each and every transistor. But until or unless you do a step down in the V-curve, you do not get the details. That means at higher level of the V-curve, in the left hand side, you have the abstractions. It involves creating higher level representation that captures core features and functionality of something while leaving out of the intricacies that are not relevant to the context. Now, why I am spending so much words and so much text and infographics here? Because once you enter into a VLSI company, it's like a factory. So there you will not have the time to digest all the meanings. So before going there, you should digest all the meanings and you must have all the things in your mind. Once you are stepping into a company, you are on a live project, so you understand everything in the wink of eye. So I am preparing you for that particular moments. And as an engineer, that time you will operate very smoothly. Abstraction does not eliminate the complexity, it just focuses on what's important on a particular purpose. In the V-curve, right, there was multiple steps like this. So each step, what is important is defined by that level's abstraction. So this is an abstraction level 1, abstraction level 2, abstraction level 3. So these levels all are called abstractions. But abstract at different level of the V-curve means different things. It's like looking at the world through different lenses, each revealing a specific facet. That means, say you have multiple lenses for your microscope, right? They can have 10x zoom, they can have 20x zoom, they can have 50x zoom. All those lenses are different. And when you see through one particular lens, you get some amount of detail which you do not get by the next one. Hence, each and every lens has different detailing or different level of detailing for you. Abstraction is that kind of a lens. Next, abstraction is a powerful tool for managing complexity, encourage understanding, and enabling innovation by allowing us to work with complex systems without being overwhelmed by the minute details. In couple of slides back, we had the V-curve and there was lot of infographics, and each of the step means you are plunging a more deeper level where the details are much more in quantity. Abstraction helps a designer for this step-by-step design process. It hides unnecessary details at any particular step, and it helps to manage the entire design complexity. Think of a time or think of a situation when you do not have the abstraction. That means you see the entire chip in terms of the transistors. What will happen? You will be confused and utterly demotivated to proceed in the design. To stop those demotivation, the concept of abstraction is brought into the VLSI design and through the V-curve. So there may be other mechanisms other than V-curve or the Y chart give you the concept of abstraction. You may find, so these are different methodologies, they can be coexisting, and I do not have a debate with them. Each and every different methodologies to depict the abstraction is okay, and that may be important in that particular part of the VLSI. So this is the concept of the abstraction. Now let us move on to the next slide. Now let us see the abstraction levels of the design. Behavioral domain is all about how a system functions. We imagine a part of the design as mysterious black box and focus on the relation between the input and the output. So this is another word, the black box. We have each and every block or sub block of a design, right? That we think as a black box. It has a set of inputs and it has a set of outputs, and that is how it meets our expectation as a designer. In structural domain, we describe a system by its different parts and subsystem, as I have shown in the V-curve infographics, right? Geometrical or physical domain gives information on how the sub-parts can be seen in a structural domain. Now let us have another infographic. This is a very generic thing that you will find maybe in your textbooks. So we have a system, then we have a module, and then we have a gate, then we have a circuit, and then we have a device, or next we have the layout. So this is the different abstraction level. So this is first abstraction level, this is the second abstraction level, third one, fourth one, fifth one, sixth one. So this way the different abstraction levels are present in the entire VLSI design flow. A designer at this level understand by abstraction say A, B, C, D, but a designer at this level will not understand abstraction by ABCD. He may understand it by KLMNOP. I just give some even random words to explain this. These don't have actual meaning, but just to understand. So here it is ABCD and here it is KLMNOP. These two things are different. You can understand by the alphabets that I am using. But the abstraction means something at each and every level. And that means it is hiding unnecessary things. That means here if we have detailing as of this level, then the designer here will be demotivated, and the next level designer will be demotivated if we flatten all these things. Now I have just talked about a term which is called flattening. If we do the flattening right up to this level, the designer here will be confused or demotivated to anything further, and at the final stage when it is for tape out, the entire abstraction concepts are flattened to get your chip. So that is actual thing. So that flattening is done by the PNR tools and corrected and verified by the sign-off tools. Now we talk much further here. Level of abstraction could be defined as the amount of information that is hiding within it. Higher levels of abstraction means less detailed a level is, so more information is hidden. So here the information hidden factor is 1000x, here it is 100x. Okay, so like that you will have some factor to define the different. So here you will be seeing that different level of abstraction and different amount of data is hidden. So data hidden here is different, data hidden here at this level is different, data hidden at this level is different, data hidden at this level is different, and here it is much hidden. This is called the level of abstraction, and this makes a designer life easy. Otherwise each and every designer has to know about everything from top to bottom, and the design will get stuck, it will not get tape out. Very simple. So we have different level of designers. Some are transistor level designer which may work in the standard cell team, and some are like digital design engineer which work in the HDL design part or the RTL design part. Some of them could be analog designers who are designing the analog part of the circuit as a block or subchip. This way different designers are needed in actual one particular VLSI design. So this way the entire chip is designed by dividing or subdividing the entire chip into different blocks and giving each block to each particular team to design and realize. And finally the PNR and the sign-off team, they actually flatten the entire thing, which all level of abstraction they get from different design teams, and finally they flatten it and test it as a system, as a prototype as I have shown you, and then they go out for the fabrication. Here, lower level of abstraction means more detailed a level is. That means as we go down here, if I draw an arrow, the more detail we are getting. System or processor level is the highest level of abstraction. So this is the highest level of abstraction, and this is the system or processor level. Switch or transistor or circuit level is the innermost level of abstraction. So I said here it is the transistor level, and in the synthesis generic term I have also shown you, right, there is a layout synthesis process also. This way the abstraction defines at different level. Why I am talking so much about the abstraction? Because when the optimization, different optimization inside the synthesis engine you will come across, you will be correlating these concepts to those particular optimization. What optimization is done for which particular step, that time that mapping you will be able to do. We are done. Let's move on to the next slide. Y diagram, the coexistence of domains. So in this chart, we'll briefly talk about the Y diagram, on which we have a detailed episode. Here you can see the thumbnail we have just depicted. In case you want to have a detailed understanding of the Y diagram, please go ahead and watch that particular episode. That will help you to understand the different domains, that is the behavioral domain, the structural domain, the physical domain. Understand it. It is well explained in this video, but here I will touch base some of its points which are talked in that particular video as adhesive, which works as an adhesive in this particular synthesis tutorial in terms of the V-curve, the VLSI design flow, and the abstraction. So let us start. Helps us to understand digital hardware design. So this Y chart helps us in this particular purpose, and it correlates the different level of abstraction among the structural, behavioral, structural, and physical domain. Three axes represent the three domains of the VLSI. Behavioral, what a particular system does, that means what is its behavior. Generally this starts with the AGLs. Structural, how the entities are connected together, that means how these chips or subchips or maybe unit circuit components, how they are connected, right? Physical, how to build a structure on silicon, that means the layout level. So here you can see that different things are there. Here you can see transistor layout, standard cell, macros, floor plan, block or chip, chip or board. And in the structural domain we have the CPU, the subsystem, ALU, gate, and transistors. So you can see the color combination. Here it is purple, so it is purple. These are blue, so these are blue. And here these are green, so this is going to the behavioral. So you can understand in this fashion. Has the required connectivity to implement the behavior. So you can see by following one particular circle, right? If you want to move from behavioral to the structural, if a system specification, if you go down, it will be again the V curve, right? And once the V curve is completed and come up, right, in the same level, these circles are at different levels. So here, if you go from this point to this point, the system specification in the structural domain, it is the CPU, memory, or IOs. And in the physical domain, domain. It is like chip or board, right? Those things. So this one. Now if you see the algorithms at this point, if you go by this here, it will point to the subsystem, FSM, all data paths, right? And if you come by this line here, you will see what the block, chip, etc. all these things in the physical domain where the transistors are there. So this way you can see what levels of the V curve. So you can see this is a 3D V curve. You can say it's a 3D V curve where the center is at the bottom and the levels are at different level of heights. You can see the V curve in flat 2D as I have depicted few slides back, and it's a 3D. So Y chart is a kind of concept where you can imagine a 3D or you can concentric circle you can see, and each point of intersection will be at the same level at different domains of the design. So hence I was talking that the VLSI design is a very complex thing. It has to be understood by the abstraction level, and hence you may come across that a question every time you are there, maybe in a company you are searching for jobs. So what is the difference between digital design engineer and a physical design engineer? Both are design engineers, right? They design at different level of abstraction. That is the difference. And also we have a detailed episode on this particular job roles. You can go ahead and find out that in our channel. So here we will go further in the bullets. The next one is the 5 concentric circles represent 5 level of importance in the design. That is the system, algorithm, RTL, logic, circuit, etc. So these are very important 5 circles. Outermost circle is the most general, and each circle closer to the center represents a smaller and more specific part of the design. That means once you go towards the inside, right, you are descending through the V curve of the VLSI design. So as you go inside, you are stepping down as part of the V curve, and from here as you go down, you are stepping as per the V curve. And again, this is not the stepping down. So in the V curve, when you rise like this. These two you step down as the V curve, and this one is you go up. The 5 main characteristics at each level of the abstraction are basic building blocks: signal representation, time representation, behavioral representation, and physical representation. So there are several types of representation which are used to realize a concept of a chip. That means a specification, that means the text specification that you write with pen and paper into an actual silicon chip with maybe large number of legs that goes into a circuit board. So for that, this particular conceptual breakdown is needed, and that's why we talk about so much about the abstraction, the V curve of the VLSI design, and the Y chart. I'm done here. Let's move on to the next slide. Mapping of levels and domains. In previous slide, we have shown multiple things. Now let us go this mapping. You will find this slide also there in the Y chart episode. If you want detailed knowledge, go ahead and watch that particular episode. So here you can see that we have our abstraction level and different domains: behavioral, structural, and physical. So you see the 3 axes of the Y chart here. Now system or processor level, right? It is there. Behavioral, it is represented as written spec. Structural in terms of module, and physical terms of physical partitioning, talking about the layout here. And here we are talking about module and chip algorithm architecture. So here behavioral, it will be algorithm, flowcharts, etc. Structural, it will be processor, RAM, ROM, and physical, it will be clusters. Functional or RTL, if we have the abstraction level of this, so what will mean? The data flow, register, transfer, and structural, it is ALU, mux, register, etc. So now you can see, if I have just shown you this before the Y chart or before the V curve of the VLSI design, if I have presented this slide at the very beginning of this presentation, right, that time what you will get confused. Now you are able to correlate all these things. These are all the concepts that exist in the VLSI, and here in the column, right, in this column we have different abstraction level, and each column we have behavioral representation, structural, and physical representation. So for functional, if to be a physical is a floor planning and standard cell. For gate or structural logic, we have Boolean equation as a behavioral. Structural, we have AND or XOR, etc. And for physical, we have state cells, that is standard cells, module, and etc. Now switch or transistor level, abstraction level, if it is the abstraction level, then behavioral, we have different equations, and structural, we have transistor, resistor, capacitor. Those are fabricated into silicon and they have electrical characterized properties, which you will find in the .lib file, and we have a detailed episode on .lib. You can find it in the STA playlist. And here in the physical level, it will have the mask geometry. So this way you can understand different levels of the abstraction in the entire VLSI design. I'm am spending so much word so that the entire complex VLSI design flow can be understood by you in simple terms. And once you enter, maybe here, maybe in this team you are getting a job versus you are getting a job here in this team in a different company versus you are getting a job here in a different company. So you will be able to differentiate between this design engineer post, this design engineer post, and this design engineer post. So there will be 3 different design engineer posts, and with this particular chart you will be able to correlate that where you are getting placed. And once you are inside the company and you identify that, okay, I am at this particular design stage in the team, right, you will be knowing from where other things are coming. So who are the neighbors and from where you are getting what, following the V curve, not this chart. If you are in a company and you get allocated in any of this particular, say, zone, so using the understanding the V curve and the Y chart, you will be knowing that who are your preceders and whom you are delivering your content to the next level. So this is very important. So we are done talking about the different level and their mapping, and if you suddenly placed into a particular block, how you will find who are before you and who are after you in the VLSI design structure. For you, this is the concept, and you will be able to differentiate between different design engineering roles. So we are done here. Let's move on to the next slide. HDL compiler versus synthesis compiler. These are 2 types of compilers, and in this series we will learn about the synthesis compiler, and in the Verilog episode we have shown you the HDL compiler. You have to able to differentiate in between the 2, and hence I am proceeding with this particular type of infographics. What is the difference between the HDL compiler and the synthesis compiler? So first you will have your Verilog description that you are writing by your hand about the target specification that you get. Maybe as a student you can have a small cell, or you are inside a company, that time you will have a complex set of targets written in Verilog. Maybe system Verilog could be there. So for simplicity I have kept Verilog. Next, as we proceed, we will use the HDL compiler to transfer this particular Verilog into a translated design. That means this is used for simulation. So once we get translated design, it is ready for the simulation, from where you get the 0 and 1 graphs, which you may see in the GNU plot. An HDL compiler is an example like iVerilog, Icarus Verilog. And as we move further with the translated design, what we have, our synthesis compiler, that we are going to learn in this series. And the synthesis compiler will convert this translated design with the help of the PDK and the DK. PDK means what comes from the foundry, and the DK means which have the standard cell library and other necessary blocks which are there packed into one particular package and given to you as a PDK or DK, whatever nomenclature any company is using, by including all the details of that. That means when the synthesis compiler starts working, first it has to look for this one. Without that it cannot proceed, and without this particular, that means the translated design, it also cannot proceed. That means it's not a standalone tool that converts this into the next step, but it will need definitely the PDK or DK where all the standard cell definitions are there, and with the help of that it will do the technology specific synthesized netlist in terms of physical gates, and say you are doing it for 22 nanometer or 10 nanometer. So that particular library will be there. The Verilog description does not have any technology node attached to it, but however that will get attached here through this library, the ASIC library. Generally it is called the ASIC library, PDK or DK, and using that library your synthesized netlist will be, say you are using 10 nanometer library. So this will be a 10 nanometer synthesized netlist, but here there is nothing about the nanometer, and here even when you are doing the HDL compilation there is nothing about the nanometer. Here it is first step, you are approaching towards the fabrication because you are using the library which is supplied by the foundry. That means you are stepping into the first step of the chip fabrication, and hence it is not very same with the general HDL compiler, which do not have any technology attachment to it. So the technology attachment here is done. So once you use the 10 nanometer you will get the 10 nanometer. So in case you are using a 22 nanometer library, right, so it will be a 22 nanometer synthesized netlist. This way you are proceeding or approaching towards the actual fabrication. So we are done here by making you understand the difference between the HDL compiler and the synthesis compiler with respect to the basic ASIC library and the technology nodes for fabrication. We're done. Let's move on to the next slide. Here we will go a very brief thing. In your company, you may see about any of the infographics, maybe this one or the next one in the next slide, as the VLSI design flow to understand the synthesis, right? So that's why I have kept both versions so that you do not get confused. So this is a brief VLSI design flow, which is, you can call an abstract art of the VLSI design flow. And the next one is a detailed art. This is an abstract art, right? Let's start. Here first will be the specification. Next, as we proceed, will be the high level description, and next we will have the RTL netlist. Specification is pen and paper as the first step of the V-curve. Then we have high level description. From that specification, you think of something like FSM or something like that, and then you code it into the RTL netlist. And then you will have the process of logic synthesis to convert it into the technology bound get level netlist. So this is technology bound. So it is tagged as a 10 nanometer get level netlist or 22 nanometer get level netlist. So this is technology bound. So next we will have the layout synthesis again, which is technology bound, and there you will have the physical design and verification steps. So as you go further down, this your synthesized netlist will be further provided to the physical design team. They will go for the layout synthesis, maybe for the 10 nanometer process or 22 nanometer process, whatever you are doing. Or it could be nowadays maybe 5 nanometer. Okay, so whatever you see and go, they will go in that direction in the technology attached manner. So hence you see the first, once it's all these are done, right, it will go for the fabrication step for the technology means. I have kept the color same here where there is no technology attachment here, and I have kept the green color here for which are technology dependent or technology tag is attached to them. You understand that the synthesis is the first gateway or the doorstep or the first step of the staircase, which allows you to enter into the fabrication step. This is why the synthesis is very important in VLSI. Now we are done talking in a very short and sweet manner about the VLSI design flow. Now let us see VLSI design flow in a detailed manner. So let us see where our synthesis is there. First we'll have the design specification and our flow will proceed in the downward direction. And next we have the RTL coding. Next we have the design verification, that is DV. Then we have the synthesis. So this is the synthesis we are talking about so much. Next we have the DFT or scan chain, the DFT process, that fault detection that I have talked in the initial slide. Next we have the fore planning. Here we are entering into the backend part. Next we have the power planning and routing. Next we have the global placement, all those things globally placed. It's a kind of major or rough placement. And then we have the detailed placement. So that means the actual detailed placement. And then we have our clock tree synthesis. That means the clock should go to every block which needs the clock. And then in this upward direction, our flows goes this particular flow. That means it will go starting here and then it will go in this direction. Next we have the global and detailed routing. Next we have the layout generation and changes. So there will be iteration. Maybe these two steps will have multiple iteration. These two steps will multiple iteration. These two steps will have multiple iteration. Similarly here, these two steps will multiple iteration. You don't know whether it will go here or here or here. It depends upon what type of modification that iteration is causing or what type of error is coming and at what level you have to go back. Now here is DRC and LBS. Next we have the parasitic extraction. These comes under the physical verification part. Then we have the static timing analysis. Also there is another static timing analysis happening at pre-layout stage. We are not shown it here, but it is there. But mostly the static timing, this static timing analysis will take the parasitic netlist and take the effect of the actual effect of the parasitics. We have a detailed series and now we have marathon on static timing analysis. In case you want to watch it, you can go ahead. Next we have the EM and IR analysis. We also have detailed episodes on both EM and IR. We have LEC and final tape out checks. Finally, we go for the tape out. Also to mention, we have, I think, design rule check. So this is the DRC design rule check. We also have a detailed episode on that. You can go ahead and check that. So this is the entire VLSI design flow breakdown. I think I have given the almost every step. Some tips maybe break down further. So at least for this particular slide to contain, I have stuffed it this much. So in our series of synthesis, we will be focusing on this particular synthesis and we will not go any further down. So that means we are not talking about all of this. But the importance of this particular synthesis is that we are getting ready with our design, right? Whatever design we have done in these steps, design and verification, we are getting ready to step into the actual fabrication step. So that's why the synthesis is very much important, because this point onwards we will have the technology node maybe 5 nanometer, maybe 10 nanometer, maybe 22 nanometer. Whatever nanometer technology node you are using, that time you will be getting attached to the technology node, and the constraints and design rules, all those things will be coming into picture. So it is not there you have a kind of free road or maybe where you are driving. So there will be a congested road where you have to drive carefully. So synthesis is the step from where you have to be very careful about the technology related data. That's all here about the VLSI design flow, and just move. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.